Welcome everyone. Today we are going to do a system design for the problem called Ticketmaster, following up our Stripe system design, which is performing extremely well. I'm so happy that people liked it. We are going to do exactly the same way, going really down to the technical details and what is going on under the hood, why we made this or that decision, stuff like that. So let's start. As usually, we are going to follow our well-defined structure, which is define functional requirements, non-functional requirements. Then we are going to implement the functional requirements. Then we are going to implement non-functional requirements. And the first point is typically follow up, like infra cost, deep dives into some component, whatever. So our functional requirements basically mimic the real Ticketmaster app, which is create events for the performers and managers, search for the events for the consumers, for our basically buyers of the tickets, book and pay for the ticket/seat. Note that we are going to interchangeably use term ticket and seat because these are pretty much the same. And the most important requirement for us, this is semi-functional, semi-non-functional requirement, which is about avoiding double booking. This is one of the core requirements in this system design, and this is what interviewer would like to see you solving right now. So let's start with functional requirements first. So our first requirement is to create events. Let's go simple way. We are going to have just one client. We are defining some API. Let's name it events API. This is going to be simple HTTP server, RESTful, whatever. We are going to define post endpoint for events. And let's say we need to store it somewhere. So of course we need database or storage. All right, I think with this way we kind of implemented it. Let's maybe define what data we are going to store. So for sure we need event model or entity. And for sure we need to define our ticket/seat. I'm going to use a seat entity, but you can use it ticket as well. So let's define it with basically event ID and ID, which are two unique identifiers of the seat. We need also status to understand whether it's booked or free. Owner ID, this is optional actually, because if seat is not booked, it doesn't have owner ID yet. And update that, we're going to use it a bit later, but yeah, we will need it. Now we are going to implement search for the events requirement, which is going to be just one more HTTP endpoint that leverages query parameters, and by these query parameters we can translate them to some SQL or any other database language to query the events that we actually are interested in right now. So pretty simple, we don't change anything right now. Then book/pay for ticket and seat, and for this one we actually might need an external service. In our case, we are going to reuse our previously designed problem, which was Stripe. So we are going to use Stripe, and now we are the customers of the Stripe, we are the merchant now. So Ticketmaster is actually a merchant of Stripe in our case. Yeah, let's mark it as an external dependency here. How it might look like, so let's maybe try to draw a simple user experience UI to see what endpoints do we need. So we're going to have first screen, user just enter the application and he or she sees a bunch of events, and let's say the user clicks on this particular event. It moves user to another page with performers, some details, arena map with the seat map on top of that. Now user is able to click any free seat and it redirects him to additional page, which is page where he fills the payment details, like card details, who is the user itself, address, blah, 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 and there is a button called click. And then when we click, we are actually going to perform a transaction to the Stripe and fill in the update to our database that actually this user is now owner of this seat ID because he just paid for it. So next screen should be success screen, and that's it. Now, what endpoints might we need in this case? So for searching the events, we already got one endpoint. Then we need one endpoint for retrieving the exact event related details. So let's define it. So it will return to the UI the seat map, arena, number of the seats, specific details about event. Basically, these two entities all together are attached to specific event ID. Now, what we actually need to do is before the actual payment, user should be able to select a seat. And this can happen on the UI side purely. So between these two screens, we might not do any request to backend. But this won't work, and I will explain you why within the next few minutes. So let's say this is happening on the UI, and we are calling the backend when we press button pay. So let's say here's some endpoint post for the specific event, I don't know, booking. And this is like what this endpoint should do. Basically, it's pretty simple. We should go to database. We should check whether status is still free, and this seat doesn't have owner ID yet. So basically, for booking, we also need to add seat ID here. Then after this first step, we are going to perform a transaction to Stripe. Let's say Stripe returned us 200 OK. And as a third step, we are going to update the database back and set owner ID as the user that just paid on the webhook from the Stripe, and set the status of the book. So when the next user is on step 1, it sees that this seat is actually booked, and step 2 and step 3 is not happening. But this won't work on the concurrency. This won't work if two users clicked the seat pretty much the same time. And here is why. Imagine that actually two users clicked on the same seat, because for now this seat is free. They clicked on the same seat. There is user 1 and user 2. Both of them are going to retrieve details from the database, and both of them are going to see status as free. Both of them are going to perform a transaction and actually pay for this seat ID. Both of them are going to get a webhook, not them, but our API, webhook from Stripe about success of both of the transactions. And then both of them are going to update the status to booked and set owner ID as the user who actually did the transaction, which will be in the webhook ID. And what will happen in the end that actually this user, let's say he paid $100 and this user paid $100 as well. But in the end, only the latter update will put owner ID as the one who is owning the seat. So let's say user 1 was the first one and webhook for this user came first. We update owner ID to user 1 and set status as booked. That's okay, but then we got second webhook from user 2 and we are updating status to booked, which is already this status, right? And we put owner ID as user 2. And user 1 now spent $100, but he's not owner of the seat. And when he came to event, he basically will be kicked out. This is not good. For sure, this is not good. How we can solve it? So for sure, checking the status after the read in database, it's not feasible. Like it's not possible to be correct at that point. Checking the status after the transaction happened, it's also not feasible because we already did transaction, like money is gone. What we can do now is try to refund the user and stuff, but this is not the ideal way. So what actually we can do and what Ticketmaster does. Whenever you click on your seat, and this seat is free right now, Ticketmaster gives you 10 minutes timer. Why? You might ask why. Because this is the moment that you are actually locking this seat from anyone else. So once you clicked on this seat and whoever clicked on this seat the first, this guy is going to spend maximum 10 minutes on filling the payment details, getting his bank card working correctly, doing transaction stuff like that. All other users, they won't see this seat as available. Even if they see it because of the glitch of replication delay, whatever else, they won't be able to enter this screen as well because it is exclusively locked for this user. What we can do right now in our simple design, we can add one more endpoint, which is events ID logs seat ID. Not the best RESTful design, but still. This endpoint is called whenever someone is clicking on specific seat. This is the time when we are going to database and we are trying to set our status to neither free or booked, but to locked. So we set our status to locked. And after that, what we want to do is to not allow any other user after that to set status to locked. Basically because it's already locked. Any other user should see the status as locked and not be able to set it again. Let's say right now we are emulating two concurrent requests again. So we have our user 1 and user 2. They both want to pay $100. And we need to be very careful with this to not allow double booking again. How it can happen? If we are doing again the same approach that we're reading from database, checking the status in the code, in the events API process, and then we are doing something based on that, this is wrong. This won't work. Why? Because let's say we are again reading the database, both threads and both users will see the status free. Both of them will try and set status to locked, and both of them will succeed because actually this is idempotent operation, right? Update SQL statement is idempotent basically. When we have concurrency and we need to lock something exclusively, what you can do is to apply either pessimistic or optimistic concurrency. So pessimistic concurrency in this case would be to basically exclusively lock particular seed with some seed ID. Let's say we want to have seed 5. So how we can do it? We can use select for update SQL statement if we are talking about SQL databases. This will exclusively lock the row for seed with ID 5, and no other user will be able to write or update this row until the transaction is basically done. This is how it looks like. We are doing this statement, and then after that we are performing updates, seeds, and setting status for specific seed 5 because we just locked it due to the statement for update. Optimistic concurrency approach would be a bit different. Now we don't need transactions at all. We can do it in separate transactions. So how it will look like? We are trying to update it straight away, but we are updating using optimistic concurrency, which means that we are updating seeds. We are setting status equal locked, where ID equals seed 5. Seems the same until exactly that point, where we check status still equal to 3. So this is tricky thing, and you need to know a bit of database knowledge and how database would handle that. But basically, since every single update statement in a nutshell is going to be a separate transaction with default isolation level, which is read committed, this will work. Because then on your code, you're going to have rows affected variable that will tell you whether this update was successful or not. And if your rows affected is actually 0, it means this update didn't work. It means that somebody just already set status to 3. And that's it. And basically, based on these rows affected, you can already know whether your update was correct or not and whether you should proceed with the payment or not. Simple. How to choose between these two? In general, pessimistic concurrency is a bit heavier. Optimistic concurrency is a bit lighter. But how to choose between them is actually explained in the Data Intensive Applications by Martin Kleppmann. Basically, you make a decision based on contention. If you have a lot of multiple threads trying to write to exactly the same seed, in this case, you're choosing pessimistic concurrency. If you have a couple of threads in the edge cases trying to write to the same seed, which is our case, then we should choose optimistic concurrency. Why? Because optimistic concurrency triggers retry in case of failure. So if rows affected is 0, basically you need to return the error to client, and client will try again later on, right? So it increases the amount of operations. Also, optimistic concurrency is a bit lighter. So in our case, let's for now proceed with optimistic concurrency, and we can discuss later how it is going to look right now. So let's say we are getting exactly same 2 concurrent requests from user 1 and user 2. They both going to perform this SQL statement. Let's say user 1 was the first one. Then it will go here, it will set status to locked, and that's it. Now this thread for user 1 is going to proceed with try because it knows that, yeah, he got the update and he's the one who is doing the booking right now. By the time user 2 reached the events API, this user 2 thread will go here to event storage. It will try to execute exactly the same SQL statement again. And what will happen is that actually this statement will return rows affected 0 because database would see by the MVCC or any other, if it's not Postgres approach, that status is locked in the current version of the event storage. So that's basically it. Database would do this update atomically because this is database. It's pretty clever. So user 2 will see rows affected 0, and it will return straight away as a failure, I don't know, 400, sorry, this seat is busy, try again later, and stuff like that. So we basically avoided double booking for now. Simple, but we have one problem. What if user 1 actually clicked on the seat, we put the status to locked, and this guy just disappeared from internet, or he went for a coffee for 1 hour. This seat will be locked forever, and it means we will never sell it to anyone else. After these 10 minutes are gone, somehow we should update the status and set it from locked to free back. Unfortunately for Postgres, what we can do is only to spawn some additional background job, some worker that is going to scan our SQL database based on the status. If the updated add happened more than 10 minutes ago and status is locked, set it to free again. Since I had multiple system design solutions before, I know where it goes already. And typically when you need exclusive locking for some specific resource or row in your system design, and it should be scalable, most of the time you can just say one word, distributed locker or distributed lock approach, and you will be 100% correct. So what is the distributed lock? It's exactly the mechanism in the distributed systems how to solve problems like that, to allow only exclusive access to specific row or to specific scene in your system. In our case, to the seat. So how it works, there are multiple implementations of distributed lock. So one of them is actually using RedLock, which is locking based on the redis. Why redis? First, we don't have concurrency problems because this is single-threaded storage. Second, it has native mechanism for TTL, so we don't need to have any additional worker. The rows will be disappearing on their own. Third, it's pretty cheap. So how it's going to work right now and how we are shifting our locking behavior from the event storage to RedLock. Keep in mind that now we should force Redis to use file sync to every single write because we cannot lose this data. Now the RedLock becomes basically storage rather than cache. So how we are going to do it? Redis has a native operation which is atomically sets some key in case this key does not exist. Set if not exist operation. This is atomic, we are not scared of some concurrency because this is single-threaded and stuff like that. So how it's going to be happening right now? We have user 1 and user 2. Now first, before attaching anything of these two, we are going to write to RedLock, to our Redis instance with operation set if not exist and seat ID. In our case, this is seat 5. What Redis is going to do is basically, if seat 5 is not in the set of the keys, it will set it. If it does exist in the set of the keys, it will reject the operation. So let's say user 1 is the first one, he will set the seat 5 to the RedLock. User 2, who will be the user after one, it will go, try to set it and gets the rejection, and we will go exactly the same way back to the client that, sorry, the seat is busy, try again later. Once we successfully set the seat 5 in the RedLock, what we can do is basically start doing our thingy on the Stripe, perform some transaction, update it status here. An important part here is actually to update the RedLock and reset this TTL, because keep in mind that we are setting this key only for TTL of 10 minutes. There are a couple of problems with this TTL actually, because if user is pretty slow and we are approaching the edge case when the amount of time since we set the key is actually 9:59, if at that point user just started initiating the process, we will still allow it, right? But by the end, the user paid and is on his way to update the event storage, there might be another user who will try to set the lock, and it will be successfully set because the TTL by that time would be 10:00 and the row will disappear, or sorry, key will disappear. In order to prevent it, there are multiple approaches. One of them is to actually prolong TTL if the user is active. So client might be checking if the user is doing something on the UI, and we might have some endpoint that actually prolongs this TTL further to 10 minutes, so it doesn't disappear. If user is completely not doing anything, you just say, okay, sorry, you will lose your lock soon. Another thing we might do is actually first thing that we are doing after we got the webhook about successful payment is to update this to booked. And we also will add operation before going to the RedLock and trying to set the key related to seat. We actually can go and just perform single read to our database, checking the status whether it is not booked already or not locked already. This is only for catching the edge cases. In general, the approach first writing to RedLock, then writing to Stripe, then writing to our database, then writing back to RedLock, removing the TTL, is actually working approach, and this is how we are going to do that. Okay, and this way we actually solving both requirements, which is booking the ticket and avoid double booking because of our distributed lock. One more thing to mention here, that actually this problem might be solved also by using third-party mechanisms like deduplication on Stripe side, because Stripe receives something called deduplication key, which it will be using for actually detecting the same payments to avoid double charging on the Stripe side. So we can put our key as an event ID and seed ID, and if two users concurrently try to pay with exactly same deduplication key, and it will be same deduplication key if they use the same seed and same event ID, Stripe will reject one of the payments, and this is what we can actually handle here. And this is how we can reject one user, the one who was late, that sorry, we didn't charge the money from you because somebody already purchased this seat. Sorry, you gotta be trying again. So this is also something that should be used in hybrid with the RedLock and with all our things that we just designed. Okay, let's do our non-functional requirements right now. And what do we have here? We have high load, which is 710 million daily active users, which means like on average we don't have that big load. Most of our problem would be spikes, like celebrity problem for Taylor Swift, Lady Gaga cases where we have 3.5 billion requests during the period of booking. So it can translate to 50 to 200K requests per second, which no storage can actually handle, and we're gonna discuss this problem later and prove that actually we cannot solve it by regular scaling at all, and we will need to use another third party, but we will talk about this later. We want to be as high available as possible, as always. We don't want to make our system down. And with regards to consistency, we want strong consistency for booking, for sure, because we want to avoid double booking, right? For that, we need to put linearizability requirement. But we can be eventually consistent for everything else. So for event creation, for example, we might be fully eventually consistent. We don't care that some created event will appear in the search result in 1 hour or in 2 hours. We don't really care about this case. So we can relax our consistency requirement here. Let's try to scale and keep in mind availability and consistency at the same time. So let's first try to scale our API. Scaling API is pretty trivial thing because API is stateless. It means that we can put API to the cluster and spawn as many instances as we want, because we can kill freely one of them, we can spawn one more, and nothing is changed due to this. Actually, scaling events API like that by introducing more replicas fulfills our availability requirement as well, because if one instance dies, another instance will pick it up. For sure, like we are leaving load balancers behind the scene because it's pretty trivial. We're just spawning a bunch of the load balancers and we will be updating them using some algo. So yeah, load balancer is not a single point of failure as well. Now, let's think about our event storage. And event storage is not that easy to solve. First of all, event storage should be linearizable. Why? Because it contains information what seats are actually booked. And this is information about money. This is information about our correctness. So whenever we are writing something here, we should be actually not losing the data, at least. And not losing data requirement is already not that trivial. I'm not necessarily telling we should be exactly linearizable, because what we are doing, we're essentially just writing a request, and we ensured due to our distributed locking that only single user can write booked status here, because only single user is going to get a lock from the RedLock, right? So we can ensure there will not be any concurrency, which actually allows us to go slightly more relaxed than consensus like RAFT. Let's see. Before that, I think we need to actually separate this storage to two storages because we are having our search, and search might require a lot of indexing because we can get a lot of filters, right? Maybe even full text search, and indexing makes our reads faster but writes slower. Since we would like to have our writes as fast as possible, especially in the Taylor Swift case, Let's separate search storage and event storage to separate storages. So good. Now search storage is going to have just basic event information. We don't have all details in this event. We, for example, don't have seeds in this scene. Yeah, and now we can try to scale this scene together. So for search storage, we scale it by adding more replicas because this guy is extremely heavy in terms of reads rather than writes. We don't have that many performers adding new events, but we have a lot of consumers that want to search for event. So we're adding just a sync leader follower replication. Why so? Because we are okay with losing this event information. It will be detected and user will just add this event information again. And by doing this async leader follower replication, first of all, we ensure it will be highly available because we have multiple replicas. If one guy dies, another one will pick up. Second of all, we have pretty light writes because we don't wait for other followers, and these followers can die as well because we're asynchronously waiting for the replication. So this thing is trivially solved. It also means that we are going to do a double write because now we need to add event here and event here. It can be done by using Kafka and putting event to some queue, and then some worker would read, and it will ensure that event ends up in the both storages. Or we can do just dual operation and first write to this guy and then write to that guy, because that guy anyway can lose data and this guy cannot. So by the time we are writing to the search storage, we for sure know this event is already here. Okay, I hope we solved this and we are good with this approach. Now, with the event storage, we actually want to be scalable. And one of the main scalability approaches is sharding. Why we didn't apply sharding here? Because we don't have sharding key. We are searching for all events, and sharding won't have any optimization here. But in this case, we are mostly targeting specific event. We're either reading from this event storage to get the details or writing to this event storage because we just made a transaction. So it means that we can shard by event ID. For rebalancing, you can use either of three, like rendezvous hashing, consistent hashing, or redis hashslots approach. Choose any, it doesn't really matter. So this is about the scalability, but what about availability? Like let's say this event storage is handling event 1. If it dies, there is no any other storage that can pick up the event 1. So for replication and high availability approach, what we can use here is leaderless replication. Why so? Let's actually discuss our approaches here. So we can have a sync leader follower replication, same one that we had here. It doesn't fit our requirements because it can lose data on the leader election. So we don't go with it. We can have sync leader follower replication, which actually waits for all followers to catch up with the writes, which means our follower might die and it will block the whole availability of the system. So explaining right now. So let's say we have leader, we have follower, and with synchronous replication, leader is waiting until follower accepted the write. So if follower dies, and we have some writes to the event storage here, these writes, they will be timed out because leader cannot sync, and so it cannot acknowledge the write. So it won't work because it doesn't provide necessary availability requirements. Next thing, we can have multi-leader replication, which actually can lose the data, and it is not that linearizable, that meaning that we might have two pieces of the same data in two different storages. And you remember we have this thing that we actually want sometimes for the edge cases to read the status here and see that it is booked. And if it is booked on the leader that just died, second leader won't show this seat at all or show it as a free, which will allow some edge cases to have a double booking. So multi-leader is not something that we want to have. We have last approach, which is leaderless replication, which means by having a good quorum, which is write plus read more than n divided by 2, we should have a quorum where we have successful writes plus successful reads more than half of the nodes in the cluster, basically. Leaderless replication is good because most of the time it has a recency guarantee if we keep this quorum. So we will have a most recent update. There are some edge case that allows us to actually lose data a bit, or not the data, but lose an update, a specific update. This can happen in case some specific replicas are down in between of the operation, and then when we merge the data together using some CRDT approach, or just last write wins, whatever, we might discard some changes that happened before, especially with the presence of the clock skew. But this is pretty cheaper than RAFT, which is our last option, consensus replication, which ensures both no data loss and linearizability, but it is extremely heavy to implement. It costs you money and it costs you latency. There is actually the last approach, which is just accept CAP theorem and agree that if we have a strong consistency, we cannot have high availability. So sorry, yeah, you're going to be down if you want to have strong consistency. Sorry. So in this case, I would proceed with leaderless, just with the fact that we don't have much of the concurrency here. And it means that we won't have data loss. And most of the time, we will have this recency guarantee. It is very improbable that we are going to lose some data update. And next up is actually our core storage here, which is our RedLock, and this is the trickiest one. So let's go by our list again. We cannot do async leader follower because we can lose data. We cannot lose data with locking, sorry, because it will lead to double booking. We cannot have a synchronous leader follower because it will not be available. We cannot have multi-leader because it doesn't have recency guarantee. We cannot have leaderless because it might discard your changes. There are only two options. Either we are implementing RAFT algorithm based on RedLock, so the consensus or Paxos or any other consensus algo here, which is we can do, and it will ensure that we can lose up to 49% of our nodes. So if we have 100 nodes, replicas, let's say we are crazy, we can lose actually 49 out of 100 before RAFT will stop accepting the writes. Unfortunately, it is extremely heavy, it will cost you money, but it will give you some availability. Other thing that you can do is accept CAP, and basically you don't replicate at all. So these two things and decisions you should discuss with your interviewer, and he should tell you what to do better. If you have infinite money, I would go with RAFT for sure. Now, this is in terms of availability. What about scalability? Again, we can use same approach as with event storage. We can add more shards, and we can shard by seed ID because we don't have anything else. So shard by seed ID. Great. And replication, we choose RAFT here, or no replication at all. Good. So far, so good. We are putting it to one logical thingy. Great. So now, actually, I think we replicated pretty much everything. As I mentioned before, in some cases, we might want to have a Kafka here. For example, for creating events, when we need to sync one write to populate the side effects, which are writes to this storage and to this storage, we can solve this one by introducing the Kafka, because it will be hard to coordinate, right? So instead, we can do Kafka with at least once guarantee. This is pretty much optional, but if you introduce the Kafka, you also should talk about scalability. So for Kafka, we can add more partitions as well as more replicas. It will be pretty trivially solved. For rebalancing in this sharding, we don't need to introduce any consistent hashing or something like that because Kafka doesn't have a rebalancing problem as database has. We don't need to reshuffle all the data between the partitions. Now that we solved all our requirements, let's try to solve the last follow-up, which is spikes, Taylor Swift / Lady Gaga celebrity problem. As was reported during the Taylor Swift, overall, the system had 3.5 billion requests. According to what was estimated, it translates to 50 to 200K RPS per second of the spikes, which means, assume this thing is going here. Of course, it will be evenly distributed on API level, so it's not a bottleneck, but yeah, imagine these guys are handling 200K RPS. But you can say it is sharded, right? It's per seat. So if you have 200K seats, let's say divide 200K by 200K, you're going to get one request per second, which is nothing, right? This is in case of the extreme scaling when we have single node per single seat, which will not be in reality, but let's say. There are 2 million people who want to buy a ticket Taylor Swift, which is pretty realistic number, I guess. Let's say they all go and they see the arena map and all of them clicked on some seats. And let's say these seats got distributed So overall, our system survived this. But what will be the next? Let's say you have Arena and everything is grayed out right now because first 200K people already clicked on some seats and they are locked. But then there are 1 million people who are still waiting, consistently refreshing the page in order to see some new seats that are available right now, either because 10 minutes TTL passed or because somebody changed their mind and they don't want to buy ticket anymore. So let's say there is single seat appeared available, and let's say 50K people refreshed the page and they saw this seat as available. All 50K people will try to click on this seat, and what will happen the next? Guess. It will be distributed on the event side evenly, no problem with that, but since we are sharded by seat ID, all these 50K requests, they all will go to exactly the same shard of our RedLock. And 50K RPS is not something that our system can handle. And no system can handle 50K RPS. Sorry, not system, but no single node or no single server or no single database. So seems like this won't really work because of the bottleneck on the locking side. So what is the solution? Actually, the solution is to use a third-party virtual waiting queue, which is something that Cloudflare already has. And probably if you try to buy a ticket for Lady Gaga, when you click on this event, you won't go to the Arena page yet. You will go to separate page, which will look something like that. There is queue, and it will say you that, okay, you have 3K people in front of you, so please wait until they are done. And then you will be allowed to see the Arena and try to book the seat, right? So you will be waiting on this page until this 3K becomes 0, and then you'll be allowed to this thing. So what is virtual queue and how it works? Basically, it will be something like extremely clever rate limiter. So all our requests are going to go through this third-party element called waiting room. This waiting room will ensure that only, 10K requests per second are going to be allowed to our system. Or we can ensure, for example, that, 1K per event or per seat. We can configure it as we want. So the thing is that we can set some hard bound of how many requests per second we allow to our system. And this basically solves all our problems. One problem with this approach is that actually you won't tell your interviewer how the virtual waiting room works. First of all, it's a separate, hard and complicated system design. Second of all, there is no solution on the open internet. There is no one covered this problem extremely well that exactly shows that, yeah, this thing can handle, 2 million requests, and it can distribute it by some key, whatever. So in case you're interested in me designing this virtual waiting room, because I already did it some time ago, please let me know in the comment section. Otherwise, on the interview, I would say that, yeah, sorry, this is third-party system. It is exactly the same size as Stripe, so we won't have time to design it. But there is such system. Cloudflare supports it, so this is what I would do. And interviewer most probably will be happy with this. Okay, I think we covered pretty much everything that I wanted today. Thank you so much for your attention. Please leave the feedback below if you liked it or not. And yeah, suggest the next system designs that we should do. It was me, Andrei, and see you.